Hello and welcome to my CCNP version 8 Enterprise Core Networking lecture review. My name is Arthur Solomon and I'm going to be providing you lecture material for the ENCOR 350-401 exam. So this is going to be several video lectures covering the individual modules or lessons for the CCNP material. So let's jump in and let's see what we can do. Alright, Chapter 1, Packet Forwarding. In this chapter, we are going to be looking at basically network devices communication and the forwarding architecture. So these two main sections are, again, focusing on that Layer 2 perspective and the router forward traffics from the Layer 3 perspective. So again, looking at Layer 2 and Layer 3, looking at both frame forwarding and looking at packet forwarding based off of the different layers perspectives. We're also going to look at the forwarding architectures that will be the mechanism used in routers and switches to forward network traffic correctly. Alright, so going back, network device communication, again, this is going to be the connectivity between devices. Everything we're going to be talking about is going to be within that TCP/IP range. Oh, not really range, but using that protocol suite. We should all be familiar with the OSI model, our 7 layers, top, down, application, presentation, session, transport, network, data link, physical. This is a CCNP level, Cisco professional level course, so that means you should at least have some basic Cisco associate or Cisco admin experience. So again, dedicated courses on these 7 layers. But as a review, going from the bottom up, Layer 1 being the media type and the connectors, Layer 2 being the hardware addressing. Actually, I'm going to grab my pen. MAC addresses. Our logical addressing, so IPs and path selection. It says routing of packets, yes. Path selection. Routing of packets is that path selection component. Layer 4 being end-to-end communication. Layer 5 being the trackets of that end-to-end communication, specifically tracking of packets. Then we have Layer 6 being our formatting of data and encryption, and Layer 7 being the application. That's going to be the interface, receiving and sending the data, more based on the application. Like a web browser, for example. These 3 areas are typically going to be composed of data and how the application actually handles the lower portion. An interesting thing is, again, our interconnecting or our media, and then the upper layers are going to be more of our host connection. So we should be familiar with the collision domain and basic forwarding, but we're going to go through it just in case. Data link layers are looking at the addressing beneath the IP, again focusing on that media access control or the MAC address. Again, this is going to be what is used for local communication. The IP protocol is for the communication between hosts outside of a network. All local communication is going to be looking at that MAC address. So you can have other data link layer protocols, not just Ethernet. So while most commonly we look at the Ethernet MAC address or the Ethernet frame using the MAC address, we also have things like frame relay or other layer 2 protocols that might use that MAC address slightly different. The MAC address is not part of the Ethernet component. The MAC address is part of the layer 2 component, It's just when we look at an Ethernet frame, we look at MAC addresses. That's going to be the more common layer 2 platform. All right, so moving forward, we have our collision domain. A collision domain is when we have two items communicating at the same time on the same session or stream for that media. So again, overview, we should have what's known as CSMACD, carrier sensing, multiple access, collision detection, which is a random timer component. So if a collision is detected, the devices will sense it, will do a hold down timer, and will resend with a random timer. That way you don't have two things communicating at the same time. Basically, devices should only be able to transmit or receive one at a time. So when we look at that and we go, well, a modern network, that's not feasible. Correct. When we have a hub, everything uses that same session communication, or that same session on that cable. A hub does not do anything other than take the signal and reclone it. So we have a giant collision domain with a hub. As opposed to a switch, each individual port is its own separate collision domain. Because the way the switch operates is it looks at each individual port and it only communicates with items that it's supposed to. So if PCA is trying to talk to PCB, then only those two ports will be involved, thus not having to worry about a collision from PCC. Could a collision still occur? Yes. They're far less likely to occur. The switch is smart enough to look at what's communicating and actually do their own appropriate hold down timers, so that if PCA and PCB are both trying to communicate with one another at the same time, then the switch will receive data on their respective ports and forward accordingly. So collision domain on a hub versus a switch. Remember that a hub will broadcast all data that's received on any port out all other reports minus their receiving one. So when we have an unknown unicast flooding occurring, the packet will contain the destination MAC address, and the switch will use the information it knows to forward the unicast messages. If the switch does not know it, then the switch will do a broadcast or something else to actually obtain that information. So a unicast message flooding will occur when the packet contains the destination MAC, and it is not if the switch's MAC address table. The switch will forward the packet out every port if it's not part of the MAC address table. So it will be received on this port, and if it doesn't know it will be forwarded out all other ports to build its MAC address table. Again, assuming it's not in the table. With just generic traffic flow, the switch table should be populated. So the switch table should start filling out. So that's how the MAC address table is done. That section's for unicast. For broadcasts, the broadcast traffic in the network is intended for any host and all hosts of the LAN. So the switch will receive it and then again forward out all ports. Normally that could be a source. So we're actually going to look at this. So source would be 0C15 0 or C0 00 11 01 destination That's the broadcast address. That way the switch can receive it and go, oh, that's broadcast out all ports. Important to point out, in a collision domain, broadcasts do not cross a layer 3 boundary. Broadcasts domains, meaning a layer 3 boundary will exist on the layer 3 devices. Normally we say router, but also a layer 3 switch. So again, broadcasts will not go past a layer 3 device. So how does this work with virtual LANs or VLANs? So adding a router to a LAN segment to help shrink the broadcast domains. Again, notice that last we were talking about collision domains. That collision domain, once we go to broadcast, that broadcast domain is the sphere that will handle our broadcasts. Again, that layer 2 section. So we can add a router between physical LAN segments, but that might not always be feasible. So we can actually logically separate them by using VLANs. So when we are looking at our VLANs, logical separation by creating multiple broadcast domains on the same physical switch. So when you are looking at a frame header, there is the 802.1q fields, and we know that VLANs are defined by the 802.1q standard, which does state there's 32 bits that are added to the packet header. Have to love the word how they use packet header frame to the following fields. We'll have a tag protocol identifier. Non-Cisco devices, they use the word tag or untag, where Cisco also has tag and untag, but they also have a VLAN ID. They also have, generically in the 802.1q field, a priority code point, so a PCP, a drop eligibility indicator, DEI, and then they also have the VLAN identifier. So when someone asks, well, why are VLANs between 4,000 or between 1 and 4096? That's because this 12-bit connection, or the 12-bit portion of the header detail, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 3, 4, 5, 6, 7, 8. That's the 128 spot. 256, 512, 1024. Oh, I'm definitely miscounting. $2,048. If you go to the 13th bit, that would be 4096. So if you look at the 12 bits, if they are all on, 2048 plus 1024 plus 512 plus 256, yada yada yada, that is going to be 4095. And if we can go between 1 and 4095 potential VLANs, that's what gets put in that VLAN identifier section. So people will then ask, well, why did I go 13 bits when there are only 12 bits there? Because when you look at the binary math, if you have an additional bit, whatever number that is, all previous ones, or all previous bits before that, if they are all turned on, then it'll be one less than that additional bit. This one is 4096. If all of these are on, is one less than 4096, which would be the 4095. That's how I got the 4095 quick math. How to create a VLAN? you get to your privileged exec mode. From there, connect to your terminal. So you'll be at the global configuration. Again, this part right here denotes that you're in global configuration. You can identify the VLAN by just typing VLAN, or you can treat it like an interface, so VLAN. So that is identifying and setting up the VLAN. This part is actually using the VLAN as an interface. If you're just setting up a VLAN, you can give it a name, a description, things like that. To view any of this, you could do a show VLAN brief, show VLAN ID, give it a number, and you can summarize it. So the output should be split into 4 main sections: VLAN to port assignment, system NTU, spanning session, and private VLANs. Interesting. If there's a private VLAN, is there a public VLAN? The answer is yes, there are public VLANs. And this is way outside of the scope of this specific video, but there is additional videos on the advanced switching that covers private and public VLANs. So if we're looking at show VLAN, we can see the additional portions of that. So you can do a brief, which is only the relevant port to VLAN mapping. Show VLAN summary, that will display a count of VLANs. Show VLAN ID and give it an ID. And then we have our name VLAN, and it will give you the output from the original command, but filtered only the VLAN names that is specified. So honestly, I find it best to actually show this. So give me 1 second. Alright, so I'm going to hop in, throw in a switch, throw in 2 computers. Get this guy all wired up. Alright, so I'm going to get to my switch. So I am trying to remember to do increased font sizes, so it should be a larger font size than what you're used to seeing. I'm going to get to my global configuration. Alright, so from here I'm going to do VLAN 10. Name student. I'm going to set up VLAN 20. Name teacher. Alright, so I want to do my show commands. Show VLAN. So I have the details of my VLAN. So I can see all my ports are attached to my native VLAN. So I'm going to go ahead and fix that. Conf T interface FA0/1 switch port mode access switch port access VLAN 10 exit interface FA02 switch port mode access switch port access VLAN 20. Alright, I want to do one more. I want to do my show commands again, so I'm just tapping enter to get everything off my screen. Show VLAN brief. No, sorry, show VLAN. I just want that. We have our 2 VLANs. Their ports are now showing in the correct area. We can see the VLAN IDs, the types, the SED, the MTU, and any of the other items that are necessary. We can see our primary, secondary types, These VLANs are active and typically not used. They're for FDDI, token ring, older technology that are still here. It is important to note, if I delete VLAN 10, the port does not automatically go back to the default. You actually have to migrate the ports if you are going to be deleting a VLAN. So that is something to keep in mind. Alright, so we said show VLAN gives you this detail. Now, let's do it again. Show VLAN brief. It will show you just the brief without all of the other specific details. Tap enter a few times. Show VLAN summary. So actually I'm going to just do VLAN question mark. You'll notice you don't get a brief summary. If we do brief, we do question mark, we don't get nothing. You'll notice in packet tracer, the summary command is not here. We get brief, ID, and name, so that's what we'll do. Up, show VLAN, brief, we'll do ID next. You actually have to give it the ID, so if you want to see VLAN 1, VLAN 10, VLAN 20, you can be specific in the VLANs. So next, again I'm going to do question mark. VLAN name. Again, you can't just say name. Teacher. It will show you the details of the VLAN named teacher, or whatever the name may be. So with show VLAN ID or name, they essentially will show you a specific VLAN that you identify via the number, ID, or by its name. I think this is easier when we're talking about some of the commands that actually show you, not just talk about them. So that at least covers our show VLAN brief, ID, and name. Sadly, with packet tracer, or at least my version of packet tracer, the summary command is not here. Alright, now let's move on to access ports. So when we're configuring an access port, again, you create the VLANs, and you just seen me do that. I created the VLANs, and then I had to move the individual ports to a whatever appropriate VLAN is. So I'm going to grab my pen, create the VLAN, navigate to the interface, switch port mode access, VLAN, give it a number. And then repeat. Now you can also give it a name, but you have to declare it as a name. So name, and then that also works. And I didn't mean to cross out the 99. I'm just saying you give it a number. In this example, they're doing it by 99. Switch ports on most Cisco switches are layer 2 by default. If you actually have a layer 3 switch, you can actually turn off that by no switch port. And again, we have a dedicated module on advanced switching to cover some of this. So now, what about trunks? What happens if we have multiple switches with VLANs on them, and we want VLAN 10 to communicate with VLAN 10 on another switch? Well, that means we need to set up a trunk. We do that by navigating to the interfaces on both sides and changing them to a trunk mode. So let's hop into packet tracer and let's do that. I'm lazy, so I'm just going to copy and paste. Alright, so first of all, what type of cable? Like devices means it should be using a crossover. Now move over to our global configuration, get to the gig02 port, switch port mode trunk. Now, I just shortened it, but switch mode trunk. I'll type out the full command on the next switch. Enable comp T and gig0/2. Oh, there we go. Switch port mode trunk. Now we could do other things, like we could say only allow VLAN 10 or only allow VLAN 20 or allow all VLANs. We have a lot of things that we could do here. So let's actually investigate. Switch port mode question mark. We could do some additional criteria. So if I just do switch port, notice I'm actually going to go ahead and make this big so we can look at it. We did switch port, we did mode, and then we could say access or trunk, but we could actually do trunk after we've changed the mode, and we can say allowed or native. So we can do some VLAN controls here. We can say allow VLAN 20. And that means they will only allow whatever VLANs you have flagged as that approved VLAN or VLANs. So if you only use VLANs 10, 20, and 30, you might do allow VLAN. So it'd be switch port trunk allowed. You know what? Let's type it out. Allowed VLAN we can add all, except, none, or remove. So we're going to go add 10. Oh. All right, let's try that again. So switch port mode, trunk, add. Oh. Switch port mode. I did too many up, sorry. Switch port trunk. Allow. VLAN. Add. 10 space 20. Notice you can't do that. Could we do 10 comma 20? No. Can I just do 10? Sure. Can I go back and do 20? There you go. Now let's see if that actually works. Do show run. You notice it shows just switch port mode trunk. And up here they are showing. So let's actually look at the interface. So do show. You know what? I'm actually going to exit, show VLAN. Again, that shows our VLANs. Show. Do we have a show trunk? No, we don't. So there are some additional commands that we got to look through. Show interface trunk. So here we have VLANs 1, 10, and 20 on those ports. We scroll up. We did the switch port allowed VLANs 10 and 20. So now let's look at if we did not do anything. Show interface trunk. right now it only knows about VLANs 10 and 20. I just wanted to point out that you can control what you put on this VLAN, or what you put on this trunk in regards to VLANs. So when we're configuring trunks, don't think that you're required to have all VLANs. You can say all, or you can be specific, or you can exclude. Alright, so moving on, we have our show interface trunk command. You can see what VLANs are allowed on which ports. You'll notice port VLANs allowed on trunk, those are the VLANs that we allowed. So I bet it didn't like the way that I did it, so it didn't actually record here, which sometimes that's just what it is. You can control the VLANs. At the end of the day, that was the point, so we're good. All right, moving past, we need to look at this native, because here's our management. Here's our native VLAN, meaning what? What's the purpose of the native VLAN? So, the native VLAN, according to the 802.1q standard, all traffic that's not advertised or received on a trunk port without an appropriate VLAN tag will be tied to the native VLAN. By default, all switches use native VLAN 1. All switches, Foundation, Juniper, Dell, Netgear, some random brand, the native VLAN there out of the box should be VLAN 1. And again, when any traffic that's advertised or received on a trunk port without a VLAN, we're going to assume belongs to that native VLAN. So what exactly, why does this matter? So when the switch has two access ports configured as access ports and associated with whatever VLAN, in this example VLAN 10, a host attached to the trunk port with a native VLAN also set to 10, the host could then talk to the devices. Whatever the native VLAN is, that's what is going to allow it to communicate with the other VLANs. That's why actually ensuring that your trunk modes are protected and secured are kind of important. If the native VLAN should match on both trunk ports or traffic can change, while the connectivity between the hosts are feasible, assuming there are different VLAN numbers, this causes confusion for the network engineer and not the best practice. The native VLAN should match on both trunk ports. The native VLAN should be configured separate from all of the data VLANs that are out there. A native VLAN is a port-specific configuration, and you can change it with a switch port trunk native VLAN ID. And that way, data flowing through the VLAN is then modified. If you pull the switch out of the box, everything is going to be VLAN 1. So the native VLAN will be native VLAN 1. So when you have a trunk port between two switches, everything is still using VLAN 1. So that's why it's saying that if you set a trunk mode, or you set up a trunk, you can still communicate through that trunk because everything is going to be the same VLAN. That's why you should separate out the VLANs. It's also a basic security to do so. So moving past that, let's go back to that allowed VLANs. So you'll notice when I did it, switch port trunk allowed VLANs 1, 10, 20, 99. You can't do 1, then 10. So let's actually see what happens. So we will go ahead and get logged back in. Conf T, up arrow a few times. So, allowed, instead of saying the word add, I'm just going to go 1, comma 10, comma 20. Oh, I gotta navigate to the right port. I purposely earlier added the word add because what happens if I forgot? Let's say, oh, well, I did 11020, but I also needed 30. So now let's do our interface, or sorry, our show interface trunk. Add is after the fact. You identify what VLANs you want, and so when you do your switch port trunk allowed VLANs, that's your first time doing it. 1, 10, 20, so forth. If you do another allowed VLANs, it will replace that. So the add allows us to add to that list. Or our remove will allow us to remove from that list. Remove 30. So you can add and remove after the fact. You're not limited to just one. So again, you got lots of options here. You can do switch port trunk allow, and you can say what you want. You can add all, you can add a specific number or range, and so forth. And again, the add allows you to add additional ones if you already set up your lists. MAC address table is responsible for identifying the switch ports with the appropriate VLANs that a device is associated with. The switch will build that table based off of the source MAC address and the traffic that it receives. So when a switch is first powered on, it doesn't know anything. It has to learn based off of source addresses. This information is again maintained in a MAC address table and is used to shrink the collision domain in a switch to a point-to-point communication. Again, a few slides ago when we were talking switching with a unicast, if the switch doesn't have the MAC address in the table, it will then flood, like using a broadcast, to all of the other ports to identify the destination MAC address, to build that MAC address table. To view the MAC address table, you can do a show MAC address table, and then you can say address MAC address or dynamic or things like that. So the show MAC address table address will display the entry that matches an explicit MAC address. Dynamic will display the entries that are dynamically learned and not statically learned. We're not going to go into that. Or we can also look at the VLAN specific information. So here is a show MAC address table dynamic. You can see all of the dynamically learned MAC addresses and the ports. So when we're looking at this, we can see, I'm going to grab my pen, port 3. All of these are learned from port 3. That probably means port 3 is used to connect to a different switch. That way, that explains why multiple MAC addresses. That way, when we're looking at, oh, well, you need to communicate with that specific MAC address, we know to leave out that gig port and forward it to that other switch. The other switch, I'm going to call A and B. B switch will have its own MAC address table that it will then be able to map to the appropriate MAC addresses on this guy. All of this is stored in Content Addressable Memory, or CAM. So sometimes it's called a MAC address table or CAM address table. The CAM does have high-speed memory that is used for more faster access. It is faster than the computer RAM, and it's used for searching. The CAM tables provide a binary result, yes or no, true or false. That's it. We also have, again, different port statuses. So we can look at show interface and name it to an interface. We can see if the port's up, if the port's down. We can see the specific details, if it's a VLAN, private VLAN, public VLAN, trunking, operational mode, encapsulation mode. So by examining the configuration of a switch port, this can be kind of useful. Again, some commands are stored elsewhere in the configuration, so you do have to keep that in mind. So you can do a show interface, and then switch port. That gives you the switch port details. You can also do a show interface switch port, which gives you slightly different information. Again, all of this goes back to getting used to your show commands and what output may be useful in each different show command. So moving on, we have other commands like show interface status, or you could do a show IP interface brief. This is going to show you the port, well, specifically the show interface status will show you the port name, status, the VLAN that's associated with its duplex, speed, and type. Interesting. Let me grab my pen. Gig 1023 is a routed port, meaning that it was a non-switch port. That switch port was turned off. That now is a layer 3 port. We keep saying things like layer 3 switch. Well, a layer 3 switch does not necessarily mean that the entire switch will be layer 3. Normally, we identify a specific routed or layer 3 port. So thought that was really interesting to point out. You can also see the status of them. So here we have our cables. Here we have no cables. We have a disabled port. We can see the different VLANs or modes that they're in, if it's a trunk mode. So this tells me this looks like a core switch, but I also see things like cubicle details. So, but I also see that this connects to multiple routers. So this could be a distribution or core switch for a business. Again, we can see the VLANs, the duplex, the speed. We can see the interface. Here we have a SFP, or a small form factor pluggable, or a GBIC, and that other brands may use. Basically, this is an add-on. So if there is a driver that is needed for the software, it'll state it. Otherwise, it will show unknown. Here we have an unknown. It could mean that it needs software to determine what it is. This tells me that it's a 10 gig base SR. Probably not going to be copper. Probably going to be fiber, but I'd have to look more into it. So moving forward, we can start looking at the layer 3 forwards and local network forwards. Again, some of the layer 3 forwarding logic occurs before layer 2 forwarding. So this gets really interesting. The two main methodologies for layer 3 forwarding is forwarding traffic to devices on the same subnet and different subnet. Yeah, that wasn't a complex thing. We know that when we're dealing with layer 3 data, it will either be the same network or different network. So same, different. Where local network forwarding, the two devices will reside on the same subnet. It's all local. The data is encapsulated with the IP address. the device will detect the destination on the same network. The device still needs to encapsulate the layer 2 data into the packet, known for its own MAC address, but it's still not initially known the destination MAC address. Alright, so what does that mean? So maybe I have my source IP and MAC, and I have my destination IP and unknown MAC. Well, we already know that. That's an ARP request, Address Resolution Protocol. That will try to map the layer 3 IP address to a layer 2 MAC address, storing this in an address table. So, if this occurs, ARP, because the ARP will be used to find the MAC address of the destination for the unknown MAC address. That's the purpose of ARP. The ARP table can be viewed by doing a show IP ARP, and you can list the MAC. You can do that, and it will be broken down into the first column, second column for both the MAC addresses and IP addresses. You can also do additional filters as well to filter for more information. But again, that's getting way more into the weeds than is necessary. So far what we've been talking about has been forwarding from one device to another. Forwarding normally occurs at layer 2. When we have to forward to a different subnet, we have to be careful with the wording. You can forward to a different subnet, but we often call it path selection or routing. Packets must be routed when the devices are on different networks. So we don't use the word forwarding to a remote network, we use the word routed. The data is encapsulated with the IP addresses of the destination. Again, all of this is pretty much CCNA material. A device will detect the destination on a different network. It must be routed. The device will check for a local routing table to identify next hop, and that might be in several different ways. A static route, default gateway, or a dynamic routing protocol. Alright, so let's draw this out. Let's see what the heck this really means. Router 1, router 2. We receive a frame. So we have our IP, source, destination, IP, MAC. The problem is when the router receives it on its interface, it is going to strip out. Actually, I want to some data. The IPs remain the same, assuming NAT is not involved. At each layer 2 boundary, the router, or the layer 3 device specifically, is going to strip off the information from layer 2. So when it leaves this interface, it will pack on a new frame identifying the source MAC and destination MAC. Source MAC, destination MAC. Once it gets received on router 2, it's going to remove that MAC address, because here's one local network, here's another local network, here's the third local network. MAC addresses are used for local network communication. Once it gets to the third network, again, it's going to strip off the MAC, look for the destination, and there we go. Each hop, each layer 3 network is going to be separate. Packet routing. The source device must add the appropriate layer 2 data. This destination MAC is the default gateway interface, or the exit interface, or the router's address. Once it leaves the router, this interface will now be the source MAC, and this will be the destination MAC. Here, this is the source MAC. This is the destination MAC. One network, two network. Remember that the MAC address is used for local communication. Packet routing. When we look at this, the router will modify the source MAC address and destination MAC address as appropriately at each boundary. The boundary is a layer 3 boundary. That's why the layer 3 devices remove it, because layer 3 doesn't care what the MAC address is. Layer 3 deals with the IP addresses. So again, going back to that OSI model, there's a reason we look at specifically the OSI models layers 2 and 3. We should know that we can assign addresses to a interface. Again, that should all be there. The addresses will be used to build a route table, and it will help get the routing information base, RIB. Directly connected networks have an AD of 0 for all directed connected networks. It is possible to attach multiple IPv4 addresses using a secondary command, though again you have to be mindful of when you're doing this. The IPv6 addresses are assigned with the interface IPv6 address, not the IPv4. So all of these are IPv4. Here's IPv6, IPv4, IPv6. Is there a good use case scenario for secondary addresses? That's a whole different lecture. So I'm just going to say that you can do it, but you need to be mindful of what you're going to be doing. If we are doing some form of VLAN and trunking, so maybe we have a switch. VLAN 20. We want to communicate between the VLANs. We need to do what's called router on a stick. So we do this by providing this interface with sub-interfaces. Here are the two in this example, I'm going to change these to 10 and 99. This interface, which would be gig 001, because that's what the parent interface is right there. Then we provide a virtual exit point with a sub-interface. So we say 0.1 or 0.10, 0.99. They should normally match the VLAN number. They don't have to, but they should to keep things less confusing. That is just used to identify them. Then we need to actually say what VLAN they're attached to. Encap.1q10. This says you're encapsulating using the .1q standard, and you're that VLAN. That one's VLAN 99. And then you would treat it like a regular interface. Assign an IP address or assign an IPv6 interface, and you are good to go. You should turn back on the interfaces. So I'm going to go back. One thing that this slide does not talk about whatsoever, and it's actually really, really important, is interface gig 001 needs to be turned on. If it's not turned on, sub-interfaces cannot use. A common mistake that I see is people forgetting to turn on the parent interface. What's common between these sub-interfaces? It's gig 001. That's the parent interface. Switched interfaces. A switch virtual interface, or a VLAN, or a SVI. Earlier I said you can navigate to the VLANs. Interface VLAN 10. That will create a interface for VLAN 10. You treat it like a regular interface. You can assign an IP address, you can assign it an IPv6 address, and then you need to turn it on. This is done on the switch. That way, maybe you want connectivity to that switch by that switch virtual interface. Maybe you want a way to ping it, or maybe you want an IP address so that you could remotely configure it. Setting up the VLANs with an IP address allow for this management capability. Alright, so earlier we talked about configuring a routed switch port. We do that by typing in no switch port. That turns it to a layer 3 interface. You can assign an IP address and all of that, even though it's a switch, assuming it's a layer 3 switch. Layer 3 switches just mean that you can turn on specific ports to be a layer 3 port. So some network designs include a point-to-point link between switches for routing. Some would build a transitive VLAN, associate the port connecting to the router to VLAN 2001, build the SVIs. Always a potential that VLAN 2001 could exist somewhere else, yada yada yada. Again, a huge part here is you can turn a switch port, you can turn a individual switch port to a routed port and connect it to your remaining layer 3 network. How do we verify IP addresses? Show IP interface brief. That will show your VLANs and any routed ports where you have assigned an IP address to a switch port address. Again, that's assuming no switch port command was used to then make this port a routed port. Routed port. So there are pros and cons, but again, you have to understand that a layer 3 switch is not 100% layer 3. You can make individual ports layer 3. Alright, so let's go on. Verifying address. Again, you could do show IP interface brief, but if you're dealing with IPv6, IP is typically defaulted by IPv4, so you could do a show IPv6 interface brief, and that will show you the same types of details except looking at the IPv6 material. Alright, so that takes care of the first half. The second half is going to be the forwarding architecture. That's looking at IP packet switching or IP packet forwarding. And that's the process of receiving the IP packets on an input interface or ingress interface and determining where to forward that packet or where the egress interface may be, or if we're just going to drop it. We're also going to look at the fast switching and express forwarding, so CEF, to optimize the switching process for routers to be able to handle larger packet volumes, not just dealing with a few thousand packets or hundreds of thousands of packets, but millions or multi-millions of packets. Okay, so let's talk about our process switching. So the process switching, also referred to as the software switching, it's the slow path, is a switching mechanism which is general purpose CPU. It's what the normal router has, and it's in charge of the packet switching. The types of packets that require software handling include, actually I'm going to grab my pen for this, packets sourced or destined to the router. Again, that's going to be using the control traffic or routing protocols. Packets that are too complex for the hardware to handle. Again, packets too complex. That'll be IP packets with IP options. Lastly would be the packets that require extra information that is not currently known, ARP. So these three types of packets are going to require the slower path. So software switching is significantly slower than switching done by the hardware. The net input-output process is designed to handle a very small percentage of traffic. So packets are hardware switched whenever possible. So oftentimes people go, well, how much of this is necessary? Understanding the actual inner workings of the devices is actually really critical. So let's look at process switching on the processor. So an incoming ingress packet will need to be looked at. If the packet can be done through the CEF, the Cisco Express Forwarding, this guy will process and send it right on out. If it cannot, it's going to have to do what's called a punted packet. It will be IP input and then forwarded out. If additional material might be needed, we might have to look at the combination of the route table and ARP. Again, ARP resolving the MAC addresses. The routing table is that routing information base, which is built from the information obtained from dynamic routing protocols, directly connected, and static routes. The ARP table is built from, again, things from ARP. The routing table is a combination of learned, static, and connected information. So the routing table is going to take input from the dynamically learned routing tables, the dynamically learned routing protocols, the static configured routes, and the connected routes. So within the CEF and the TCAM, the CEF, again, even though it was used in the previous slide without ever actually being identified, is the Cisco Express Forwarding. It is Cisco proprietary, and it's used for switching mechanisms. It is the default mechanism used by all Cisco platforms. The nice thing is it uses specialized application-specific integrated circuits, or ASIC circuits, as well as a network processing unit, NPU, for high packet throughputs. Basically, when we look at that, we look hardware-based routing, hardware-based routers. It is allowed to use the ASICs and NPU for fast processing of those data packets. The switch's kernel content addressable memory, or TCAM, will allow for matching and evaluating a packet on one or more fields. The TCAM entries are stored in values, masks, and results, VMR format. The value indicates the field that should be searched, such as IP or protocol. The mask will indicate the field that is of interest and should be queried, and the results indicate the action that should be taken. The TCAM operates in hardware, thus allowing faster processing and scalability than process switching. Sadly, this is conceptual. We don't get to see this occur. There isn't an easy way to show this. Basically, ingress packet will be stripped, reviewed, and forward accordingly. And normally, when we're looking at should be reviewed, we're looking at the value, mask, and results, specifically the value, so that we can look at what normally occurs. If it's a value that is known, we can skip to results and egress it to the appropriate output or area. When a router processor RP engine is equipped with the forwarder engine so that it can actually do packet switching decisions, this is known as Centralized Forwarding Architecture, CFA. CFA. For a CFA, when a packet is received on the ingress, it is transmitted to the forward engine on the router processor, and then the forward engine will examine the header and determine where the packet should be output, egress. And then it forwards the packet to the appropriate egress line to be forwarded correctly. If the line cards are equipped with forwarding engines so that they can make packets switching decisions without the intervention of the RP, this will be known as the distributed forwarding architecture. So I'm going to read that again. If a line card is equipped with forwarding engines so that they can make packet decisions without the intervention of the router processor, then we can distribute forward architecture. That's the purpose of it. So, what does that look like? It goes in. Forward engine is reviewed. If the forward engine has the appropriate information, it can just be kicked back out. That's part of the centralized forwarder. This being the RP. Now, let's look at it through a distributed forwarding architecture, or DFA. Basically, it comes in, the forward engine will look at it and figure out if it needs to be sent to the RP, or can it just make the decision and kick it out. If we can limit how much information is going to the router processor engine, then we can do this portion faster. It doesn't need to involve the RP, which operates significantly slower than the forwarding engines. There are a software CEF, also known as the software CEF, and it will build a FIB, forwarding information base. FIB. This is built directly from the routing table and contains the next hop information. It keeps a mirror image of the forwarding information contained in the IP routing table. When a router or topology changes, it also then updates the FIB. Again, mirroring what the route table has. The CEF will use the FIB to make decisions for switching. The FIB will make IP destination prefixes based off of that switching decision. That way everything is kept up to date. We also have what's called an adjacency table. This table is known as the Adjacency Information Base, AIB, and it will contain the direct connected next hop routes and the corresponding next hop MAC addresses, as well as the egress interfaces, MAC addresses. This AIB table is populated with data from the ARP table or other layer 2 protocols. So let's look at that. So here is our CEF switching based off of software. Ingress packet comes in. The ingress IP packet needs to be reviewed and is sent either to the RP or to the CEF. Here, the CEF, if it's software CEF, we can look through the FIB. FIB will be the forwarding information, the networks, the prefixes, the adjacencies. Again, that's next hop details. And the adjacency tables. That's going to get input from the route table, and the ARP. ARP is going to build the adjacency tables for it to make the decisions to kick it out. And that kick it out means exiting it the appropriate egress pathway. Basically, if an entry is missing, it is gleaned in the adjacency in the CEF. Valid FIB entries contained. Valid FIB will continue to process information by checking both its table and the adjacency table for destination information. Any missing adjacency entries will invoke the ARC process. We'll invoke the ARP process, meaning if we're missing a destination MAC address, if it's not in the AIB, then we will figure out where to go. And we do that through ARP. So again, this is software. We also have a hardware Ceph using our ASIC. Allows for very high packet rates. It's designed to do this. This is a hardware forwarding. They do have their limits functions because there is hardwired to perform specific tasks. There are different ways of processing data in different forms. So this one is very specific to ASIC. And so the ASIC is very inflexible. So the routers will also have NPUs that are designed to overcome ASIC inflexibilities. The NPUs are programmable with firmware so they can be changed easily. Packet switching is distributing, again, the distributing architecture, and that's done by distributing Ceph or dCeph. This mechanism is which the Ceph data structures are downloaded to forwarding ASIC and the CPUs of all the line cards or interfaces so that they can participate in packet switching. This means that switching happens at the distribution level, thus increasing the packet throughput of the router. Meaning we're trying to skip the router processor. Again, oftentimes we're not having to be expected to know the intricacies of switching. Just understand that there is a process that actually occurs. If you are an engineer or an architect, that's slightly different, but there's a lot of detail that goes into switching. All right, so again, getting a little bit deeper, we also have a stateful switchover. Basically, the RP is going to be learning the network topology and building the RIB. If a RP failure does occur, then it will trigger the routing protocol adjacencies to reset, resulting in the packet loss and network instability. If the RP fails, there's bigger issues. So basically the router function would end up failing. So that's what it's talking about. So during an RP failure, it may be more desirable to hide a failing network or router than to continue forwarding packets using other alternatives. Essentially, if the router is having issues or the route is having issues, it's better to hide it till stability returns and then you can use it. This is known for stateful switchover, SSO. It's a redundancy feature that allows Cisco routers with two RPs to synchronize their route configuration and control planes so that the process of mirroring information between both RPs. It's preferred and is used as a checking point, so SSO-enabled routers have the ability to have two. If one fails, the other one can kick on. During a switchover, the standby RP will immediately take control if the primary RP is encountering any issues. The number of MAC addresses that a switch needs is really based off of the function, compared to the number of route tables that it holds, depending on where to deploy it on the network. The memory of the TCAM, the memory of the CAM, is going to be dependent on the location. It is statistically allocated during the boot up sequence of the switch when a section of hardware resources is full. All the processing overflow is sent to the processor. So TCAM having the appropriate memory is kind of critical because, again, TCAM is fast. If TCAM memory is full, all of the excess is kicked over to the processor. This will negatively affect the performance. The allocation ratio between the TCAM and stored and can be modified using the Switch Database Manager templates, the SDM. That way you can say how large or how small the table should be. The SDM templates can be configured on like Catalyst 9000 switches with a global configuration of SDM prefer. And then again, the switch has to be reloaded. Sadly, I don't have a Cadillac 9000 switch, so I can't really show you that. Here's what it looks like though. Show SDM prefer will show you the details. You can actually look at the templates and the template information. Alright, that is it for this module. Key topics were collision domain, broadcast domains, VLANs, port types, access, trunk, tagging, TCAM, CAM, ARP, how forwarding and routing works, switching, all of that fun stuff. We learned a lot of new key terms. We looked at a lot of different tasks and the show commands and the different commands that are used. We looked at how to display content. And that is it for this module. Alright, so that wraps up this module. If you have any questions or concerns, definitely feel free to reach out, post a comment, ask a question. Remember, as we're going through this material, it's common to be able to take some time, gather your thoughts, ask some questions so that we can really work on retention and getting you more familiar with the material. Thank you.